from the Department of Computer Science. It's my great pleasure to welcome Jesύs Labarta. Jesús is a professor of computer architecture at the Technical University of Catalonia and director of the Computer Science Department and professor of computer architecture at the Barcelona Supercomputing Center. He was formerly the director of the European Center for Parallelism of Barcelona, and he's here today as the 2017 recipient of the Ken Kennedy Award, named after the illustrious Ken Kennedy from Rice. So the Ken Kennedy Award was established in 2009 to honor scientists who made outstanding contributions to programmability or productivity of high-performance computing, together with significant community service or mentorship. Jesús was a member of an elite group of scientists who worked on developing the roadmap for exascale computing, which is kind of the principal challenge in high-performance computing today. So that's a quest to deliver systems that are capable of performing 10 to the 18th operations per second. And Jesús is well known for his pioneering work on task-based programming models and runtime systems for both homogeneous and heterogeneous systems. This work has greatly influenced the OpenMP standard for mapping computations onto accelerators. And I know Jesús best for his work on performance tools, and he's going to talk a little bit about some of these topics today. Welcome.
Thank you, John. So thank you. Good afternoon. I'm really happy and honored to be here. And I wanted to start, I'll be talking about kind of personal vision of some of the directions that computing should be going, HPC parallel computing should be going. But I will start by mentioning a little bit my respect for Ken Kennedy. And I have to say that, so the award is to developments in terms of software and programmability. I started my life in a department which is an architecture, hardware guys, and I started doing this type of things. And essentially I moved to the dark side. So that's what they consider there as the good thing is hardware, and really we moved here to the other side, thinking there was really something beyond just pure hardware, which may end up being certainly more important, I believe. That's my belief now. But really, this is a significant kind of potential wall, which you need to, in order to jump over those walls, sometimes a little bit of help or a little bit of catalyst is a good thing. And so this is a collaboration that we had long time ago with the support. It was actually started by a collaboration with Convex, with Steve Wallach. And we work on a compiler for doing data distribution, so kind of generating from the sequential Fortran code, generating the directives for Fortran D at the time, or so. And we did this, and it was without actual direct contact with Ken or even with you ourselves. But through that indirect link, we ended up using your infrastructures and getting your support to do a work, your Ken's team in overall, to do a work on this transition from the hardware to the software side. So really for us, even if I didn't have a really lot of interaction with him, it was really something useful, something very, very helpful, and that I really appreciate a lot. I thank you. So the talk actually is what happens in then and what I've been doing. I wanted just to give a little bit generic, very, very, very general thoughts and visions, overviewing what we have been doing. But before that, because maybe some of you may not know, we are now in the Barcelona Supercomputing Center. We are running. This is a very nice. It's the most beautiful data center in the world, right? And we do have a title for that. Yeah, there's a real official formal title for that. and that's where we have our data center. But well, this is the current status of the current situation of the machine. So it's a decent machine. Over the years, we have had something at the beginning, impressive fourth position in the top 500. Then it's gone down, different versions of the machines. But well, we're probably a little bit even lower would be more corresponding to the economic power of the country. But I think we have a nice data center which is at a decent level, and which is one of the things that we operate for the service of researchers in Spain and Europe. And the center, besides that operation, the center has 4 departments that do research on computer science, which is my department. Then there's departments on life sciences, earth sciences, and engineering. And what I think we have is a nice kind of holistic environment which covers from applications now to low levels of architecture design. So this is what we are doing, but this also shapes also the type of our background, motivation, our interest is in high performance computing, in scientific, in simulation. That's where we come from, where we are from. And what I will start is by talking about a vision, a personal vision of what has happened in the last, I don't know, 10, 15 years now, probably, about computing, of parallel computing in this world. And some time ago, life was easy, okay? Some time ago, you had architectures, you had an ISA, and you had applications on top of that. It was relatively easy. No, you up here, you knew very little about what was going on down there. And what multicores brought was a leakage of this membrane, right? And you started needing a lot of knowledge of the internals if you really want to get some performance out the outside. And the result of that is that applications grow, applications fill up of if-devs for this GPU, for the other GPU, for if I have an FPGA, so the applications end up growing very much. And I think this is kind of a really important characteristic of what's going on. So this complexity, by the way, also with this complexity and variability also in the performances of the devices here, what all of this is causing is an important divergence between the way the machines behave and the way we think they behave. So in reality, we have mental models of how machine behaves, and we program to those mental models. We map things to those mental models, and in reality, the systems underneath have very potentially very different type of behavior. So what I'm trying to say is that the situation, the last years, from my point of view, what is in this context, which I would look like very difficult or negative or I don't know if this is the revolution, but it's a big issue. What do programmers need? And my belief is that what they need is a little bit of hope. Okay, is somebody who tells them, yeah, you can still continue writing programs and still be able to use this or survive in this situation. A little bit the life cycle, what is happening, what has happened with codes is that you start with an idea, but you start growing your code with more or less effort, including more or less life of code, but things start growing and growing and growing, supposedly to introduce optimizations and specificities of a given platforms or a given, and getting away from the logics of the algorithm and the programs. This is what really happens in many codes. In some cases, you just do total changes in the shapes. So you put CUDA, for example, and you start doing, I don't know, things like refactorings, which really change a lot the shape of the code. And if we keep down this ripple chain, I think it's going to be probably a very bad message. And what we try to say is that there is some possibility, or there should be some possibility, or going back a little bit towards the origin. And this is what the hope that I think we should provide to programmers is this possibility of going up there. this is what kind of philosophy. This is kind of, if you think of this as a revolution, what has happened and what we have to go back from it. This, what is the fundamental of a revolution, okay? Typically, so they may be more or less shaky. You take the French one, there may be a few heads here and there, but there's, the important thing is, well, that is important, yes, but there's fundamentally in the long term a more important thing is what is the changes in mentality from before and between before and after the revolution. So there's power emanates from the king or power emanates from the people, whatever that people is. So these are fundamental things that change the way we see the world and we look at it. So if you ask me what I think is or what I would like to be, the change in this revolution is a change in mentality from what we are today. Which I consider it, we live in the latency age to a throughput age. In parallel programming, in scientific parallel programs, I believe we live in the, and it's coming. It's coming, okay. So we live in the latency age. We live dominated by the fact that I need this and I need it very fast, and if I don't get it, I cry, okay? And this applies to caches. This applies to MPIs, latencies or MPI. This applies to the four-join models. So it's kind of, we need things and we need them immediately, right? And I think we have to change to a situation where we can state, I need this and that and that and that, and when this comes, I will need this other thing. And so we can specify things in a more generic way. So it's about instantiating lots of works and being lots of work. And then that work that is instantiated, as long as you preserve the semantics, of course, but you can execute it in ways that really, that really essentially only depend on the available amount of resources. And I think this is the situation we should go. We should tend to go to a situation where the execution essentially depends on the amount of resources. So I would now shift to the, it's coming. So, and I think this is the fundamental thing. This is what the title is of my talk, and this is what I think we should develop the technologies which are important for that, and we should develop the cultural mindset changes for getting that done. And probably that's my view today. Probably was not my view when I started working on these two topics, but I believe that these two topics are very important to achieve that. One of them is programming models, and the other is performance tools. It's understanding in this divergence between our mental models and the behavior of the system, understand the behavior of the systems, and then provide mechanisms for programmers to express this kind of throughput-oriented expression of what is the computation that you want to do. And what I will talk is a little bit about both of these topics, things that we are done, and visions, and some experiences, and some examples. But I will start with the tools domain, and I will start by looking a little bit at, well, what is performance analysis for, and probably one of the first uses is to know who to blame, right? To understand, is this a problem of my MPI implementation, or who can I make guilty of something? But we typically use here practices which have to do with very coarse grain aggregated type of evaluations. We look at the scalability, but in reality these behaviors depend on microscopic internal, very fine grain behavior of the systems. So we have one approach then, which is to measure the very coarse grain type of activity, and then we have the other approach is to go to the other level, which is too much of detail, to go to very, very, very fine grain detail. And by the way, we have been working traditionally ourselves, working in this too fine grain, too much level of detail, right? is this good or bad? What is important? And the fundamental thing is I think both things are needed, but I think the fundamental thing is being able to try and understand and grasp behaviors of the systems, fundamental behaviors of the systems, which go beyond the details of a specific syntactic expression of how a program is written, and who are much more fundamental. And and really go to the fundamentals. This is basic to fix and counteract and decide which are the best, most appropriate directions for optimizing the code. So what I think is needed is both things. And I said, traditionally, we have been working on the low level, on the detail type of thing. I think it's important to look at the high level, how to describe the performance of the application to users, to developers of the code, in ways which are abstract, simple, and easy to understand and to characterize. This is a project where we have applied and we have done services, things like going to research groups, but also to companies and tell them, we'll be analyzing your code for 1 month, 1.5, 2 months. I will be telling you the type of things that we believe happen in your code which limit your performance. And I think has been a very interesting story. And what I will tell you is a little bit the first level, the abstract level, the high level thing that we have been presenting. And this is, how do you describe the performance of the application in terms of a parallel part and in terms of a sequential part? And we are working on this model, which is essentially 6 numbers that tell you how good you are in terms of fundamental concepts. And some of these fundamental concepts are load balance, transfer, and serialization. These are metrics that describe how good, between 0 and 1, a product multiplicative number, how good your code is in some of these fundamental properties of parallelism. There is another side of the model, which is efficiency of the sequential computation parts, which has factors that include IPC. How is your IPC scaling with increased core count? Does it stay stable or not? How does frequency change? So the cores today run at the frequencies they want, and depends on. So how does that change during the execution of the application? And the final model, the final component of the model is about instruction scaling. It's about is the computational cost of your application independent of scale of the number of cores, or do you have some level of replication of the computation? So the result is that you end up with having a very simple model that characterizes fundamental properties of the behavior of your application that can be used to steer the type of refactorings that you do. Actually, what I had here is a measurement of some of these metrics, because I think it's nice, it's interesting, and the idea is how you go from the full detail of gathering data of all the activities of a program and when is every process running or waiting. How do you go to obtain these 3 numbers that tell you load balance, serialization, or transfer efficiency? And no, well, essentially the idea is for load balance. So what if this is a timeline? So you have processes here or threads here. This is time. Blue is computing, red is waiting. What is a fundamental limiting factor here? Assume that we were able to push everything in blue towards the left, do a Gantt chart of that, and this is the actual computing. All the rest would be the sum of all these holes over there. There's one guy who takes more compute than the others. So this part of the inefficiency, this yellow part is an inefficiency which is responsible of is due to load imbalance. The other part is what you can blame to computation, to communication. Yeah,
so the yellow in the middle chart is waste.
Everything yellow and red is waste, is lost time, but the nature of those things is different.
Yeah.
One of them is because there's one guy who takes that amount, the largest amount of computation. There's nothing else. If the others take less computation than that, there's nothing else we can do. And by the way, this is an interesting thing. I don't know how you measure. There's I don't know if there's a very clean. Hello. A very clean characterization of load imbalance. A lot of people say, oh, I measure load imbalance by measuring the standard deviation, coefficient of variation by the time taken by the different processors. And here actually what we end up saying is from our point of view, the right way of measuring load balance is computing the average time in blue divided by the maximum time of the guy, because this is what limits your time. This is what determines, this ratio essentially is computed by that. It's the average in blue divided by the maximum in blue. And I think this is a very simple metric that any profiler can generate. Very simple, but really is fundamental, that there's no way to get beyond that, right? This other part has to do, then you can say this is communication part. But this other part, so we have done one thing, which is to push everything there, but we have lost, we don't respect causality, we don't respect dependencies. What if we respect dependencies, we respect causality, but we move everything assuming we have instantaneous communication, instantaneous fulfillment of those dependencies? There will be some holes in between that cannot be packed anymore. So the thing is, this total time can be decomposed into those two sections, one which you can no longer compact and one which was due to. So if you can assign, you can use this, the first one to assume that this is because of transfer time, and the other one is because of serialization, of intrinsic dependencies in the code. So the result is that by profiling data, and in our case with a very simple simulation, in our case with our tools which does ideal machine infinite bandwidth zero latency, you can get these measurements. We have done this thing with Scalaska, for example, and they do end up computing the same type of information but just properly scanning all the different parts of the trace. And I think this gives you three numbers between 0 and 1, which present the performance of your application in a very, very intuitive, in a way that you can use to talk to somebody who is not in your field, which is also something typically very, very important, and who can steer a little bit the refactoring of the codes. And it's a very abstract way to describe or characterize the performance of the applications. So this was about the model. Actually, what we ended up doing in this project was based on these things, ended up writing reports to the users. I mean, 5 to 10 pages report saying this is what we see in your application, and it was pretty successful. And it has nothing to do with developing any real tool or technology. It's just applying these things in real cases. The other, and this is a very high level type of thing. The other thing that we have been that we have been doing and is the traditional kind of simulation stuff that we had in terms of separating what is the effect of latency and bandwidth in different parts of the programs. We've been doing the possibilities, and we have kept improving the possibilities of our browser to analyze and obtain very, very precise details and separate precise fine-grained causes in executions which otherwise might look. So we had an interesting example of runs on two systems which gave essentially same performance, and it actually was because of two very different reasons. And it actually was just changing, it was same source code from the application point of view, same source code. One of them, the runs, and it's on the same system, one of the runs linked with MPitch, the other run linked with OpenMP. So this is this was about the model. This is about this fact that you end up building a kind of a database of how different applications, and you can compare across different applications, how compare in terms of what is the main fundamental problem. Is it load balance? Is it transfer? Is serialization? And it's a curious thing. And the impacts on the part, let's say, having to do with the scalar performance and sometimes frequencies or sometimes IPC. So it's an interesting way of presenting at very high level the behavior of the application. Sufficient data which goes beyond just the timing of the execution of a given routine, because I mean, it's like with MPI, okay? MPI is like a perfect gas. It uses whatever space you give it. But the fact that you spend a lot of time in MPI doesn't mean that you have to go and blame the MPI provider. Maybe the cause is somewhere else. So this is, I think, fundamentally semantically different and semantically providing more insight on the behavior. Then, of course, the detail is needed for going in some of the features. And then we have these visualization tools that are able to go and squeeze and look at the detail of the behavior of different systems. And what we are seeing more and more and more is very, very strange behaviors happening in applications when you go beyond the thousands of processors in terms of behaviors that have to do with the internals of the MPI, have to do with the behavior of the locality of the processors, and have to do with sometimes things that we don't even get to know, right? So it's the machine. This thinking that I was saying before is machines behave very different from what we believe they behave. And the question is, under those circumstances that do happen, the question is, what is the best way to counteract those things, right? And this is what we'll try to do with the programming model stuff. The other thing, just to mention things that we have been doing, was if you take for every computational region between MPI calls, for example, or between OpenMP calls, it is characterized by hardware counter data. So these representations show the space-time representation of that. But if instead of the space-time representation of that, you put all of that into, for example, a space where you have total number of instructions and IPC, you start putting those things there. You end up having a whole set of data that you can analyze, happens to be have a structure. You happens to be possible to do clustering techniques, and you can clusterize that, and you can identify regions that are different between them or similar between them in terms of computational cost and performance. And so we are applying a lot of analytics type of techniques, which is clustering. We are applying techniques like doing tracking, which is what happens, how things behave in this space of instructions and IPC, how things behave when your program runs with 2 cores, with 4 cores, 8,000, 10,000. What happens there? How does computation move in that space? And because what you do is unsupervised clustering for each of those, then if you want to do a tracking, is very much the same type of things that people does in surveillance systems to track the movement of a person in a scene, for example. So we are doing this type of things, and you end up having, this is a result of that, where we are showing for 1, 2, 3, 4, 5 different colors, 5 different regions of the program, how they move in this performance space. When you increase, in this case, I think is the core count. And you can really see things that at the given core counts, regions that at the given core counts are not problematic, end up having, for example, this green one has a strong reduction in IPC when you increase the core counts. And this is only for one part of the application, which might be, if you just do a global analysis of the whole execution time of the program, these regions might be masked by other effects. This is only looking at the effects of the sequential computation part. This effect may be masked by the communications. And you end up having difficulties in understanding the details. So what we are doing, and this is something we have done in the past, we are using it and we are still doing. So can you use much more elaborated analytics and elaborated statistical methods to really understand and get insight from this? And I think this is a very, very important direction for a future, okay? So this was about the type of things we have been done in terms of performance tools. In terms of programming models, if I recall the situation that we had before with the leakage of this ISA level, what can you do or what should you do to make life of programmers easy in this way? And what we believe is essentially try to reconstruct at a higher level something that was similar to the lower level that you had before. And this should be a layer which kind of decouples what you have above it from what you have underneath it. And this should be kind of, again, a membrane where what is kind of an osmotic membrane. What passes through it is the minimal type of information that can be useful, certainly, to improving things here, but not a situation where you have to express everything that controls the inner levels and the lower levels. And we have tried to do that such a way, again, that the applications are small by implementing at runtime levels, so at runtime level, the same type of philosophies, the same type of mechanisms, the same type of ideas that people was implementing here before. What was it? This was a sequential programming language, which came out to be executed in parallel several instructions because you had all the superscalar type of execution. So what we did, we said, we start work on kind of a family of programming models, which is whatever superscalar, because we are leveraging that. You keep writing sequential programs on a single address space. The only thing is they are annotated. We don't have instructions. In an ISA, the instructions, what the instructions use and what they produce is written in a document. In this case, if you have to write programs, you have to specify in the program what are the inputs and what are the outputs. So you annotate the program saying what you read and what you write. But the program is a sequential program, and from our point of view, this is an important thing, because actually this sequential program gives a backup, an order. Order is clearly defined. What is the order? Is clearly defined. Whether the system, because of these annotations, is able to execute in parallel, great. But the order, if not, the order at least is clean. And this is what we were doing in terms of C, C++, and Fortran, in terms of pragmas, which kind of it's been a contribution and it's been pushed. Some of these things, some of these proposals have been pushed into the OpenMP standard. And what I think is important of this thing is that these annotations is the same annotation for handling concurrency and handling data access, handling locality. This single thing, integrated thing is a very, very, very important from our point of view. It's actually when in OpenMP there have been discussions, and I personally jumped in only once when if I really believe that separating these two things is a big mistake, and actually there was a point where there were proposals that were actually separating those things, and actually even today, even if the definition of the standard does not separate, they are together. Some implementations at a given point in time, they separate that information. They lose the information. Once you build the data, many compilers today, once you build the data dependency graph, they lose the information about the data. So they stay just with the dependency graph. And I think this is something which is a mistake, or at least limits your possibilities. Keeping that information down to the very end is a very, very important thing from our point of view. So this is the type of thing that we did for the OpenMP by developing a kind of infrastructure where we kind of try to run parallel to OpenMP in terms of a research platform that we explore alternatives that we try to push into the OpenMP standard. Some of them we succeed, some of them we fail miserably. Well, it's kind of the thing that we try to do. It's like when cyclists go uphill and there's one following the others. The first one is kind of pulls from the second one. There's kind of an invisible rubber that pulls from the second one and push him up. If the distance gets very far, sufficiently far, the rubber breaks and the second one will never catch the first one. Okay, so we try to do a little bit of that. And actually today we are at a situation where we know some of the proposals that we are doing will never make it into OpenMP, or very, very difficult for those to make it into OpenMP. So we are in a situation where what we are doing is this upper line, we are splitting essentially into two. We are having the OMS2 direction, which is exploring those directions which are more risky, more complex, or more, from our point of view, advanced, and certainly from our point of view useful, but you have to convince a committee, and that's, well, takes time. So we are kind of continuing that in one direction, and the other thing is some of the other ideas which are closer to the OpenMP, we're actually going to an LLVM type of infrastructure, which is easier to ensure that it's taken up. So this is a little bit the history, and I just mentioned some of the things that I believe are important, and I will comment on them. For example, regions. The fact that you specify in OpenMP today the syntax, you can specify things similar to this. All of this is in the kind of OMS type of syntax role, but You can specify that I'm accessing a sub-block of a matrix and which are the parts. This you can specify. Today's implementation essentially builds the dependencies based on the first element of that sub-block. Okay? We believe that building the dependencies on the whole, the proper specification is certainly more expensive, but it pays off a lot. That's from our perception. It lets you build dependencies in very complicated, intricate environments. Lets you do, you can write Gauss-Seidel type of codes which should traverse a block diagonally if you want to want parallelism, and if you want to write that today, you have to skew the iteration space, and you have to, all of that, you can write it without tilting at all the iteration space, just by properly specifying the dependencies. And by the way, you get, if this is inside an outer iterative loop, you end up getting the benefits that you end up having not only one wavefront, but you get 2 or 3 or 4 wavefronts running concurrently at the same time. As long as there is some separation between them, they keep going. So there's kind of side effects, benefits that I think would be very important. For example, this is one of the things that will be very difficult to make this into OpenMP. The syntax is there and is good, but making it will be difficult because certainly it's complicated and it's an overhead. But that's a philosophical thing about how important are overheads or not. The other thing which I think is important is nesting. Nesting, I believe, is extremely important. We tend to program today is bottom up, go to the innermost loops, and this, I think this is a strong mistake. And sometimes we don't appreciate, we say, oh, at the outer level we only have 2 or 3 things or 4 functions that we can execute in parallel. This is not enough. This is not enough, but it contributes. And if you have 4 at the higher level, each of them which has tenfold parallelism, and each of these tenfold parallelism, everything contributes. So this nesting, I think, is an important thing. And with today's model of nesting with OpenMP, so you can really have tasks or task graph inside the task. But there's one thing is true, that until those things, one of these tasks does not start execution, really you don't build the internal graph. So when you have an internal graph, it's not built until that is started, which means that the building of the graph belongs to the critical path of your, enters in the critical path of your computation. So it would be nice to be able to specify hierarchically, but have some mechanism to kind of explode these bubbles and dynamically let the system rebuild the dependencies. And actually, even if you have this type of behaviors, even rebuild the dependencies, explode those graphs, and build the independent dependency chains, which means they will give you a much higher level of concurrency than the current situation. And I think this is an important type of situation. Task loops is another. I'll be skipping this. Maybe the other one which is probably very important from my point of view is, what do you do if you have MPI plus OpenMP? And in today's practice, the typical practice is you do OpenMP inside the computations, and you keep sequentially the communications. But this means not only the communication, it means packing, unpacking the data, means a whole bunch of many other things, or initialization of mallocs that you do. So these things are really kept in sequential parts, which results in periods of time where you have no activity, the black thing here, you have no activity in the execution. And in fact, this is kind of, there is also a strong limitation in MPI. We say MPI is a parallel programming model. From my point of view, it's a very serial programming model. It has many things which are very, very serial. The state contained by communicators, or the state, or the fact of this matching, that this matching semantics, that the messages should be matched in the same order and as they are issued the request. So these kind of things end up being imposing a lot of order that in reality in many cases is not needed. So what we try to have is try to apply mechanisms where you really taskify the parts of the code that do the communications. You encapsulate them into tasks within the individual context of one process, and you let those things execute out of order with respect to each other inside the context of one process. the fact that there is tasks in one side and tasks in another that are related by the MPI semantics kind of establishes, so it's a mechanism that expands to the whole application level, the data flow type of mechanism that you have in a node. So it's a very natural, very simple, immediate way of exploiting at global system level the asynchronous and the data flow type of execution that you have in a single node. So this is something very important. If you do it directly today, it has the problem that it may generate deadlock, because if you don't know how long will a receipt take, and you may really generate deadlock. So the type of things that we are doing, for example, today is an implementation of a library here that intercepts the MPI calls and essentially, in a sense, virtualizes the MPI calls, so as if you had an infinite number of possible tasks executing MPI at the same time. And by doing that, you avoid deadlocks, and you are able really to execute things globally out of order at the MPI level, as if the program had been a data flow graph program at the MPI level. And I think this is extremely, extremely interesting and extremely important. It actually lets you do overlap between communication and computation, but it lets you really transform the structure of the application. It's a little bit what we said in terms of throughput oriented. You end up having lots of computations everywhere which are enabled and which can be executed in many possible different orders. And at the end, it really doesn't matter which order you execute them. It only matters that there are many of those which are potentially active. And if for some reason one of them gets delayed, or one communication gets delayed, there's network noise, well, that doesn't really matter that much, because there are other things that can fill both the computational holes in some cases and the communication holes in others. So this other thing which I think is very, very important is malleability, right? The ability of applications, so they have to be written in ways that really doesn't matter how many resources I use. The application works with a variable number of resources and dynamically variable number of resources. Some of the things this implies is forget about, so every code, whenever I look at a code and I see OMP get thread num or thread private or some of these things, I get nervous, okay? This is the programmer taking the responsibility of scheduling. And once you ask for how many threads and you use it, you can use it for the 10 following hours. And maybe the situations in the system change. And in the 10 following hours, you don't have 10 processors, or would be good to shrink your number of processors, or would be good to increase your number of processors. And if the applications have these type of features, that's impossible. So malleability is something which again is the way you use the models, in ways that the programs, you would actually, for example, require this thing, the typical thing, a single parallel with just then threads and barriers, or very big parallel force. All these things are really not that important. Overhead, and this is a kind of message that I would like to say, is overhead is not that important. Order is much more important than overhead. Much more, in orders of magnitude more important than overhead. So one of the things that happens if you have applications that are malleable is that you can dynamically change the number of cores that you allocate to each such process. And you may have regions of your program where they are serial, or you were lazy to parallelize, or they are really serial, or there is a waiting for a communication, or in those regions you can actually shift your resources from one process to another. And globally, again, we are in this situation where we are just getting throughput and making the throughput of the system process. It's not a matter of accelerating this thing, because if you accelerate, you think, oh, this is a latency sensitive part of the application, let me accelerate it. So what? When you arrive to the MPI call, you'll be waiting. You have to progress the throughput, the overall throughput of the whole thing. And this is another library that we are developing, which essentially does that. Okay, so essentially shifts cores between processes when you get to blocking calls, all the processes in the cores in the node are shifted to the other application to help to the other process, to help MPI process to help it accelerate. So this is a very important technique that does you gain a lot of performance in many applications with minimal effort, no effort from the application programmer, and which is really, we think is really an important thing. Malleability in the applications is a very, very important thing. Some examples that we had with codes that for which we had different versions. The dense lines are different versions of the code. The dashed lines are versions where we use the dynamic load balancing, and the message again is the same. The message from my point of view is not whether one version is better than the other, which is also important. The message from my point of view is that the dashed lines are almost horizontals, and what this represents is whether I use an application running with one process per node, 16 threads, or I use 16 threads with 16 processes with one node. This type of situations, people spend a lot of time configuring what is the optimal situation of the optimal, and that we believe shouldn't be like that. Should be, I have a machine, I have 3 nodes, each of them 48 cores. This is what I can compute. And really this is what we see in these versions of the code. There is some impact, but really much less than what you have on the real applications. The other thing is situation fluid couple codes with fluid and particle simulations, right? Sometimes it's fluid dominated, sometimes it's particles dominated. So what do you do in your code? How many processes you devote for one thing? How many you devote to the other? These type of things, a dynamic type of scheduling with this dynamic load balancing stuff is really very, very efficient way of making the programmer forget about what is the right configuration, right? There's a very wide range of configurations that will give you very similar type of results, not only better than the static ones, but very similar between them. And I think this is the kind of message. So let me then, so the other important criteria is heterogeneity. One thing we have to do with heterogeneity is try to make it disappear from the point of view of the programmer. And things that we have been doing is, what if this task could be CUDA tasks? The task can be FPGA code, okay? And really the structure of the program shouldn't change because of these small details. These small details are only important because the execution might be more efficient on the GPU than on the CPU, but in terms of the logic of the program, that shouldn't impact. So we have been working on this type of implementations where for a task you can provide implementations that run on the core, implementations that run on the GPU, or implementations that run on the FPGA. And the system dynamically decides which of the implementation is the best, the most efficient for that task. And you can even execute some of if you have a bunch of the gems, some of them or many of them, or the big ones will go to the GPUs, and the small ones will be executed on the CPU, and everybody will contribute. Again, is this, and the thing is, how do you express these things in a sequential? If you do that directly using the APIs for each of the models, it ends up being something explodes. That's not maintainable. The idea with these task-based models is that really the source code for the programmer is the same. It's the runtime who decides what is the scheduling of those things. So we have done that at the level of OpenMP, like OpenMP OMS. We are doing that at the level of Python, and I think this is interesting for writing or generating workflows, computational type of workflows. So we do the same thing in terms of Python. We have Python functions. We use decorators, so the standard Python decorator mechanism, and you can specify this is going to be a task, this is going to be a task, this is going to be a task. You can even specify constraints in terms of how many resources you have, and the result is that there is a dependence graph that will be built, deploy, and executed in a distributed way, even if it's a sequential Python program. And the other interesting thing here is that we implement that on top of, we support that on top of a persistent storage, object storage, so that the Python objects are can be really kept on this persistent object storage. And there's a nice mechanism to kind of multiple applications sharing that persistent storage concurrently, and you can do online type of analytics with one of the applications stores data in that persistent storage. The other one does a simple, very simple in Python syntax, very simple queries, which are really powerful because of the environment. So it's the same idea, and we have applied it to a whole bunch of applications on different areas in life sciences and in earth sciences, and we are kind of extending it, and it's being used in production in our machine. So it's an example of cooperation between different groups in the center, the groups doing the applications and the groups doing this infrastructure. So this is about the programming model. So just let me conclude saying a little bit of probably has permeated through the call, but there are some things by the time you get, when you start getting recognitions, it's probably time to ask, when crossing the door, age before beauty, right? Is a little bit the feeling I sometimes have, and I have a bit the feeling that I'm trying to push for certain ideas, certain criteria before others. In some cases, I think I have very little success, but I do think they are very important. So it's like behavior, for example, before syntax, or if we go to the programming part, work instantiation and order before overhead. I said before, people is very worried with overheads, and they're not that important. Taking a decision very, 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 very fast. If it's a wrong decision, it's not a good solution. If you take a decision a little bit slower, but it's a good decision, it's much better. And we are talking very, very fast in these things is what? If my scheduler takes 1 microsecond instead of taking half a microsecond, or takes 3 microseconds instead of taking half a microsecond, the question, so what if the granularity of the task is 1 millisecond or 10 milliseconds? The important thing is to choose the right task. It's not to take 3 or 5 microseconds. So this is a kind of message that I try to push. Is sometimes not very successful, but I think it's really very, very important. Malleability, we mentioned, possibilities before how-tos, and elegance before when they shine. Sometimes we look, and I think this happens, we look very much, oh, I got this many megaflops or gigaflops or whatever it is on this application, and we write our papers, but we don't show our code. If we were to show our code, and we were to say, hey guys, you have to maintain it in the next 10 years, maybe the balance would be probably a little bit better. So we need a lot of training and education, and try to propose and promote this type of things, which I would probably say top down. I've mentioned I think is very important. This throughput oriented, try not to stall, and this is something which is, I mean, we had the OpenMP I1, and there were proposals saying, no, I can, in this case of the graph, I can translate this type of synchronization between tasks into a task weight, for example. It's important not to stall the generation of work. Generating work, you should generate a lot of work ahead of time, and this is a mentality thing that we need to push forward. And when thinking about parallelism, we should think of potentials, and should think of, and for thinking of potential, that doesn't have to be very precise. You don't have to know exactly who goes before. You have to know, well, there are things here that probably can go, and you don't have to be very precise there. But you have to be precise in specifying. And a specification, yes, specify local means, in our cases, you have to be very precise saying what is the inputs, what are the outputs of a given task. If you specify those things right, the order of execution done by the runtime will be correct. And it will probably be very different from what you were thinking. In some cases, many times I have done a run, I've obtained a trace, I look at the order of the execution of the task, and I say, impossible. There's no way these tasks were run before the other one. And yes, it is possible, it did happen, and it was correct. So it's that the system can react to situations in ways that you had not thought when looking at the program. So let me go to my final slide, which is, it's very nice to do technologies and develop methods and runtimes and compilers and these kind of things. But the real issue, this will not change, the whole thing will not change unless we make it to change in the mind of programmers. This is really a real challenge, our educational type of challenge is the real revolution is in the mind of programmers who have to really express or accept that they will express things in these abstract ways and just specifying potentials, and they will let the runtimes execute these things in parallel. So this is the type of consideration that is done, kind of looking to exascale and beyond, but in reality it's not about exascale and beyond, it's about now. It's about using today our current machines that for most of us are not exascale nor petascale and I think this is an important type of mentality change that we have to get in the minds of programmers and in the minds of course the ones that provide their infrastructures for that, which sometimes is a chicken and egg thing, okay? But I think this is the real challenge of what we have to achieve. So thank you, and this is.
That was, I apologize for the audio visuals. That was certainly elegantly done, so I think you delivered on your last point, elegance over shine sometimes. You were elegant. So with that, let's have some few questions. So raise your hand and we'll get you a microphone. John? Here.
So when you were talking about elevating the programming models away from the architecture so that it's more malleable and easier to map onto newer generations of things, I thought you were going to make a case for domain-specific programming models, because I think that's really expressing things at sort of the highest possible level. And I was wondering, with your interactions with the various companies, whether you see that as something feasible in the kinds of application domains.
So domain-specific languages, I think are good, are important. I always say there's one risk for domain-specific language, which is start being a domain-specific language, continues being a domain-specific language, ends up being Fortran. Okay, is something that is a natural trend of every developer to increase those features. I think they are important. So what I would in my drawing, I have some of the drawings with these layers, and I put them on top, but I have in the slide, I think there are two things which are important. First, they should be easy to develop and maintain, and I think they should map, they shouldn't go through the whole, from the top, a very abstract description to the platform, to the machine. So I typically put them as our layer, for example, OpenMP OMS type of layer being the target of those things, right? But as long as they are simple to develop and maintain, because you have to do not only one, you have to do 1,000 of those, right? And so they shouldn't take responsibility, for example, of scheduling or ordering. They shouldn't, and very often people is tempted to do that. And my feeling is that they shouldn't. They should only be able to, again, to behave as a programmer, to express from a very simple syntax, or what the programmer does is from a formula in paper writes the code. So we are automatizing that level of thing, but going into this type of level. My personal feeling, if you try to go from the very high to the very end, I think it's a mistake. But the other thing is totally necessary, totally good. Yeah.
A question back there.
Is it possible to combine OpenMP and OpenMPI, which is basically a different part of the computing architecture?
OpenMPI is the MPI. It's just an implementation of the MPI message passing thing. So yes, they're the hierarchical thing that we said with this interoperability between MPI and OpenMP, and that's the type of thing. Sometimes these models, and in the current situation, the merging of those things is totally not ideal, and this is some of the things that we are trying to do with this possibility of converting, taskifying the MPI calls, the OpenMP inside one process, and letting them execute out of order with respect to each other. This is the way we think is the better way to combine the MPI, OpenMPI, and the OpenMP type of world. But I think it's not possible. It's the only way for the future. I don't see. So there's always been this discussion. So we need a revolution. You have seen I've been talking about revolution, but you will see that what I say is I'm an incrementalist. Let's say, okay. I don't think this revolution thing is going to get rid of all the millions of lines of code in MPI that you have around out there working. I think we have to provide a way for those millions of lines to become, instead of millions, million, and more elegant and with more benefits and leveraging all these features. But I think it's the way to go.
Right behind you, coming. Careful.
So, as a, I put on my programmer hat, I can embrace all of this. But time after time, I run into issues where it's the mathematical algorithms that are imposing the sequentiality, right? So people, for instance, can take, simple Jacobi iterations, and I can do multi-wave fronts and whatever. But in practice, well, you do one Jacobi pass, and then you do, in a Krylov solver, you do a global reduction, maybe 2 or 3. I get away from the Krylov solvers, I go to multi-grid, and now what I've got is global synchronization at every time I change scales, and I also wind up going from something at very fine grain where I can generate lots and lots of parallelism to a much less parallel sort of level. I can kind of get around that by solving multiple problems at once and doing them on a phase, but I just always seem to be butting my head up against, kind of this impedance mismatch with the mathematicians. Your thoughts?
I think that the difference between a very kind of bold synchronous type of algorithm with a computation phase and computation synchronization, and something that at the algorithmic level has a little bit of potential of overlapping something, and we are doing that with conjugate gradient type of variants and these kind of things. With a little bit of potential of overlapping, you end up ends up being able sufficient. This is my perception, okay? And with this approach, in large real applications, you can really get this little bit from other different places, and it ends up appearing. So I think that, of course, algorithms are very important, and if you end up having an algorithm which is much more asynchronous than the other, these things are important. But only a small additional capabilities in the algorithm to have to support asynchrony, if you are able to exploit them with a model like this, I think this makes a big difference in the result.
Any other questions? If not, let's join me in thanking our speakers.